Continuing on with atomic physics, here you'll see the IB topics that we're going to cover in this little video, and we're going to talk about the nucleons, protons and neutrons, and how those can make isotopes, how the little very simplistic mathematics works out with what those numbers are within the nucleus, and we'll also get into some radioactive decay, alpha particles, beta particles, and gamma particles. You will find that most of the mathematics that we do within atomic physics, your dog could also do, because they're just not that difficult. So let's start with one simple thing. Let me drag this on. Boom. Here's a definition of nucleon, and that's going to be the things that are inside the nucleus. There's not much. You're going to have protons, and you're going to have neutrons. That's it. Now, an important number that you need to know is the atomic number. The whole periodic table is ordered in order of atomic number, from hydrogen number 1, helium number 2, lithium, etc., etc. Now the symbol that we use for this is Z, Z if you're British, and that will tell you how many protons you have. Easy enough. Now, another important thing though is the mass number. That's the total number of nucleons. You've got your protons and your neutrons stuck together. The symbol we use, ba-boom, is a capital A to represent mass number, or the number of nucleons. Now, another symbol is we also use N to represent how many neutrons there are, and it's easy enough to always figure out what that is, because whatever your mass number is, that has to equal your protons. I'll write that in here. Protons plus neutrons has to equal the mass number. And then, the way this looks on an element, let's say you have the element carbon, 12. You can look up on the periodic table and see that it's carbon 6, and this is easy enough because you know always that this is the number of protons, this is the mass number, and you know that it must have 6 neutrons, because if you take the 12 minus the 6, you get 6 left over. Now, just to remind you, if we had chlorine 35, the 17 here, that would be the letter Z. That's your proton number. This up here, this is your A, or your atomic, or your mass number. And then if you're looking for how many neutrons, you're going to take 17, subtract it from 35, and you're going to say that you've got 18 neutrons. Now the next thing is you want to understand, if you've got this nucleus here, all of these protons are positive, and if you ask yourself how they feel about each other, well, they hate each other because they're all positive. So they're all going to be trying to blow themselves out of the nucleus. But the thing that holds them all together is the strong nuclear force. And this is like the glue that holds the nucleus together. It's only a short-range force. So if they get, a little bit away from each other, it doesn't exist anymore for some crazy reason. But within the nucleus, that's what holds it together. Otherwise, it would all blow apart. There's also a weak nuclear force that causes some radioactive decay, but we'll get to that later. Let's say you've got a big honking nuclei that's unstable. It might undergo alpha decay. And remember, this is for large nuclei that are unstable. For example, radon. It's crazy. It's unstable. And a few facts you want to know about radon is the number of protons it has. If you look on the periodic table, the Z value is 88. If you use some simple math, its neutrons, or the N value, is 226 minus 88, which is 138. With alpha decay, that's when this alpha particle just spontaneously goes boo and swims off. That's why its symbol looks like a little fish here. An alpha particle is much like a helium nuclei. And what you can say then, since it's like a helium nuclei, that means its Z value is 2, because it has 2 protons. And its N value is also 2, because it's 2 protons, 2 neutrons, and has a charge of +2. That's going to go flying off. And then you see what you have left. The original thing we call the parent nuclei. Then you've got your alpha particle, and then this thing that's left over, that's called our daughter nuclei. You always have parents and you have daughters. And the general way of doing the math, which is quite simple, so you've got your radon, and you can either use the symbol up here if you like, or you can use the helium symbol, doesn't matter. And we're going to be left with, start with radium, we're left with radon, 2, this is going to be 86. The math always works out. If you take 222, add it to 4, you're going to get this 226. If you take the 86, add it to the 2, you get the 88, which is the total number of protons. The math always works out this way. The general way that it works out is this generalization here. Pretty easy. Beta decay is a little bit crazier, maybe a little bit tougher to understand. So let's say we've got iodine 131 is our example of something that might undergo some beta decay. Let's write down its proton numbers. Protons, if you look on the periodic table, is 53. Use some simple subtraction from 131 minus 53, you get your neutron number as 78. Now, just to let you know, a beta particle is the same thing as an electron. An electron actually goes flying right out of the nucleus and has a little symbol down here as -1, up here is 0. Now, what that means is it's got the opposite charge of a proton. The 0 means it has no mass. It doesn't really have no mass, but its mass is so small it's negligible compared to the rest of the nucleus. This other thing down here, this is an anti-neutrino. And it's almost massless. It has no charge, but it has a little bit of energy. And so we know it exists because the energy otherwise shows up as missing. And what happens is the electron and the antineutrino go flying off, and we get left with our daughter nucleus here. And now what you can say here is when the electron goes flying off, we had 53 protons. Now we actually have 54. You might be like, how can we gain a proton? You can think what happens is that a neutron splits into a beta particle and a antineutrino and leaves behind a proton. Now, I don't know if that's really what happens, but you can think of it that way, and it helps keep the math straight in your head. So here we've got our parent. Here we've got our decay particles. Here we've got our daughter. The proton number went up by 1. The neutron number, since a neutron broke into this stuff, it went down by 1. So we end up with 77 of those guys. Now the math down here is pretty simple if you work out the equation. You've got iodine, and it's going to go through decay. It's going to break into your beta particle, -1 because it's opposite of proton. This is your symbol for antineutrino. It's antimatter, so that's why you put this little line over it. It has 0 charge or proton value, 0 mass, And then you've got your leftover daughter, which is xenon, which is 131. This is 54. So that's a crazy thing. Proton number goes up. The other crazy thing is the mass number doesn't change at all. The general or generic formula for this, let me see if I can bring this on, is just this here. The last or third type of radiation you have to care about is gamma decay. Gamma radiation is super exciting because that's what made the Incredible Hulk green. It may not make you green. If you were exposed to it, it would probably just kill you if you were exposed to enough of it, I guess. But it's easy to do mathematically because let's say we've got thorium-232. If that nucleus is super excited, it might undergo gamma decay. The symbol looks like a fish standing on its head. It has 0 proton value or positive negative charge. It's not charged. It's just radiation. Since it's just radiation, it has 0 mass. And you're going to be left with, you may find this hard to believe, thorium-232. You get the same thing. All the nucleus does is it gives off energy. And so you might think, well, is this really any different than when the electrons just fall down from one high level to another and give off visible light? Well, yes, because this is going to be super powerful. It's going to be in like electron volts or mega electron volts, which is way more energy than you would get from electrons. It's just this nucleus is like, and then it falls down to a lesser state. That's gamma decay.